Hi everyone, my name is Florian and I'm working as a software engineer at Google. And today I want to talk about something that I really like, it's applications. And when I say applications, it's any kind of application, but in particular the one that allow people to create things or to do things that they were not able to do before. And there is something else that I really like, it's video games. That's why I created JDevelop. It's an open source and cross-platform game engine that anyone can use to create any kind of 2D video games. Why anyone? Because it's an editor, a visual editor for games where you can create the levels of your game. And there is some kind of visual programming. I'll show an example just after. And that allows anyone, even people that don't know how to develop, to create games. And at the end, you get an HTML5 game that you can put on the web or Android, iOS, or desktop. So here is what the software used to look like. I say used to because it's the old version of the software that was created all in C++. So it's a desktop C++ application. And you can see on the right that there is a list of objects living in the game. And in the middle, you have the level of the game. So here it's a platformer. And what we want to do, as an example, is to have, when the player is stepping on the button, we want the button to be pressed and the platform that is on the right to go up in the air. So I will show how to do it using the visual programming. So here we go. I go to the Events tab, and I'm adding a new event. An event is composed of condition and action. It's a bit like a if-then. So I'm adding a new condition to check if the player is in collision with the trigger that is on the level. And if that's the case, I can add two actions. So the first action will be to change the animation of the button so that it's going to the state where it's pressed. So it's animation number 1. And I'm adding another action, which is an action to move the platform up in the air. So I'm adding to the platform a force on the y-axis. And now if I press play, the whole game is compiled to JavaScript and running in the browser. And we can verify that the button is working. So it's kind of simple for people that don't know how to program, and it's only based on logic, no syntax to learn or anything. So a few games have been done with it, so everything was working quite well. And I did the game on the top left with the cat. She's called Lil Bub. Check it out. But at some point, I had some issues. The editor was getting quite old. I had lots of cross-platform issues. In particular on macOS and Linux, it wasn't working that well. And iterating on the software was quite slow. C++. Building the UI was slow and limited to all the UI components, and honestly, the UX will need some enhancements. And the entry barrier for new contributors was quite high, C++ again. So it was time for me to react. And I was wondering, could the web technologies help? I've been doing a lot of React before at work, and I was like, okay, that's perfect for making complex UI. Or is it really? Can we have, for example, lists and trees of hundreds of elements, dynamic panels, 3D visualization, nested dialogues, drag and drop search, and all of the things that make a real application? Can we make ambitious application using React? And the same goes for JavaScript. It's perfect for most applications. Or is it really, can we reuse an existing native code base? Surely no. Or if we have advanced simulation or computation, what do we do? Or if we need consistent performance? Well, let's take a look at the code base of JDevelop. So there is the core of the software, which is composed of the C++ classes, defining what a game is, what an object, and how an event is composed of conditions and actions, and all the tools that are transpiling these events to JavaScript so that you get a running game. And on the top of this, there was all the interface done in C++ using a toolkit called WX widgets. And there was the interaction with the file system. So my first idea was, okay, let's replace the interface with React. Because I have an idea that it could be better. And for the file system, I could write adapters for Node.js or even in the browser to simulate a file system. We could run this on Node.js or Chrome or browser or on Electron so that we have a browser and Node.js and we can package the whole thing as an application. And for the central part, we could use WebAssembly to expose the core classes to the JavaScript, to the rest of the JavaScript application. So a few words about WebAssembly. It's a kind of low-level language that is running in your browsers, and it's a bit like assembly, meaning that it's not a language that you write to, but more something that you compile to. And at the end, as it's an assembly-like language, browsers are able to generate really fast execution of any program that is written in WebAssembly. And it's running on actually most browsers, most recent browsers, including on iOS and Android. So how do we write WebAssembly? Well, there is the first solution was to use Emscripten, which is what I did. It's a project that is a C++ to WebAssembly compiler. So it takes your C++ code base, run it through Clang, a C++ compiler, and translate the output to WebAssembly. There are other solutions like Rust or any language that compile to WebAssembly, or even things like AssemblyScript, which allow you to create WebAssembly using a syntax that is really that looks like TypeScript. So it's really interesting. In my case, I've been using Emscripten, and I will show you the way it works. So using Emscripten, you can download the SDK and install it. It's pretty easy. And then you're getting something called EMCC, which is the C++ to WebAssembly compiler. And you can run it on a C or C++ file. And in my case, as I have a large code base, I can replace the build toolchain that was using a classical compiler by EMCC and get at the end, instead of having a binary, I have a WebAssembly module. So fair enough, we have a WebAssembly module, which is the C++ code base compiled to WebAssembly. And we have to expose the existing classes in C++ so that we can use them in JavaScript. So let's take an example. For example, we have a class that is an objects container. So it's think of it as the list of objects that you've seen. So you can have objects and get some objects inside. And then we can have a layout. It's a bit like a level in the game, which is inheriting from objects container. So it can have a list of objects. And there are additional methods like setName, getName to change the name of the level. So once we have this, we want to write bindings. Bindings, in my case, I've been using WebIDL. So there are a few solutions to write these bindings using Emscripten. But in my case, using WebIDL, we write something that looks like, that is the interface of your C++ class. So you have to write it for all the classes in your code base. And this allows Emscripten to generate glue code that will be doing the bridge between JavaScript and the WebAssembly module. So the way it works, once you have compiled the WebAssembly module plus the bindings, is that you have a module that you can instantiate in the JavaScript engine, so on a browser or in Node.js. And when it's instantiated, you have here, it's called JD. You have this module, and you can start creating new classes, new instances of your classes, just like usual JavaScript, actually, and call the method. And it's working more or less automatically out of the box, because the primitive types of your functions are automatically converted. So depends on the language that you're using, Rust, C++, or another language. But in my case, in C++, the Boolean in JavaScript are translated to Boolean in C++, same for numbers, and for strings, it's also more or less automatically handled, so it's quite convenient. If you are passing objects to the WebAssembly method, then they are converted to a pointer or a reference in C++. And you can debug more or less using the input and output stream in C++ that are converted to console.logs in JavaScript. So with this, we have something that is running in a browser. So here is the Chrome debugger, and you can see on the top there are some output that is outputted by the C++ code base. So it's working, and then I can create a new object and call method on it. So yeah, it's working, and it's quite nice to have, you know, the C++ code base you have been writing since a few years working in a browser. There are a few things to know. First, the memory management requires care, because when you're creating a new object, it's quite interesting because it's not garbage collected, meaning that if I'm logging what this layout object is, it's actually a pointer to some place in the WebAssembly memory. So you can think of the WebAssembly memory as a huge array that is containing bytes. And when you're creating a new object, it's really creating some bytes in this memory. Meaning that if you just drop the reference to the object in the JavaScript world, the WebAssembly object will still be living in memory. So you have to explicitly call gd.destroy, well, the destroy method, to remove this content from memory. So in the case of using React or any component-based front-end framework, you have if you're creating an object when a component is mounted, you have to remember to delete it. Or you can use an effect hook if you're using React. So another thing to know is that the output files are quite large. For example, for gdevelop, it's at least 3 megabytes when everything is compiled to the WebAssembly module. And honestly, I don't really care because I'm making a kind of desktop application, a rich application. So knowing that I will package the whole thing in an Electron application that is a few hundred megabytes, 3 megabytes more or less, that's the same. And something else to know, having a complete test set is really useful because these are the kind of errors that you will be getting when something is going wrong in the WebAssembly module. So it's not helpful at all. And this can happen if, for example, you have a wrong type for a parameter, or if you forgot a parameter, then instead of getting a number or a Boolean or a pointer in the C++ world, you will get undefined, which is translated, I guess, to 0, so everything will be broken. And same thing if you're trying to use a deleted object, the native language will try to operate on something that was removed from memory, and it will crash, basically. This being said, we now have something that is working in a browser. So now, my next change was, oh, I can create an interface on top of it that is as good or even better than what I used to do in the native world using C++ before. So let's see how to do it. Again, in my case, I was using React, and my challenge was to remake all of these examples. So, for example, context menus, trees of objects, color pickers, lots of forms and buttons and property grids, all of this in the browser. So I will go through a few patterns and examples that I've been using, and in the hope that it's helpful for you. The first advice that I have is to find a component library. So, for example, Material UI or React Toolbox or Blueprints, these are examples of React component libraries. And the thing I was looking at is there an extensive list of high-quality components, because I don't want to spend time redoing all the basic widgets. I want to build an application, not to make a design system. And is there a good theming support and a good accessibility? And finally, is there some good documentation? Because the whole interface will be standing on this library, so it better be good. So I went with Material UI because it was the library with the most extensive list of components, and it's material design. It's quite good. So once I have it, the first thing I had to solve was how to display large list of objects. And when I say large, is for example, in the case of gdevelop, I have the list of objects that are living on the scene of the game, and it can be a few hundreds objects. So the solution here was to use virtualization. So for example, using React Virtualized and React Sortable HOC, you are able to do a list, to display on screen a list that is virtualized. That means that instead of having in the DOM, in the browser, to have, for example, 300 DOM elements for every object, then you will only have the objects that are displayed on screen in the DOM, so 10 or maybe 20 objects. The way it works is that instead of having a list of objects that is just mapping over an array, you're converting your list to be using the list component that is offered by React Virtualized. And using this property called row renderer, you can say this is the function that you will call to generate every line that is to be displayed on the screen. And then using React sortable HOC, you can add the sortable container HOC on the top of your list, and on the top of each element, you're using sortable element, and you get a list that is both virtualized and that you can reorder using drag and drop using the mouse or touch. So that was the first thing toward getting something that is not powerful enough, but working well even with large lists and big games. The next thing is that I wanted to have panels or editors that you can resize on screen, because as I'm doing a game engine and a game editor, people want to customize their workspace. So for this, I've been using a tiling window library, which is called React Mosaic. There are a few different libraries like this, but this is the one I've used, and it's, it's working out of the box. So check it out. Then I've been trying to remake the events editor. So the events editor, it's more or less a large tree, with this event. So an event is composed of conditions and actions, but it can also have sub-events. It's a bit like blocks of code in a traditional programming language. So here again, the solution was to use virtualization. Precisely, I've been using React sortable tree, which is a library that allows you to make a tree of nodes that you can reorder. And the interesting thing about this library is that it's using React Virtualized under the hood. So quickly, every node that you see on the screen here is actually a line in a virtualized list. And the lines that are in between the nodes is just a fake scaffolding that is making the tree looks like a tree and not a list. So it's a customized version of this that I've been using. Then at some point I wanted to remake the level editor. It was actually the first thing that I did. And at this moment, so I want to display a level on the screen, so it can be composed of 100 or 1,000 of objects to be displayed. And at this moment, you can forget the DOM. And it said, go to be using WebGL. Well, actually, I've not been using WebGL directly, but something called a library called pixie.js, which is the 2D rendering library that I've been using for the game engine. So I could as well use it for the game editor. And it's super fast and very easy to use, and it's based more or less on the Flash API. And there are other options like 3.js or Phaser if you want something that looks more like a game engine. Sometimes still you can still rely on the DOM. For example, let's say that you have an editor that is displaying an object, here a spaceship, and you want to edit the polygon that is displaying what is the hitbox for the spaceship. So what I've been doing here is to use SVG elements to display the polygon, and using things like on pointer move up and down, you can allow the vertices of the polygon to be drag and dropped using the mouse or the touch. So you get something, a polygon editor that is very easy to architecture and to hack on, because it's all done using React, and it's still powerful enough for what you want to do. Sometimes things are not fast enough. So the first performance problem that you can have is that the rendering of the application is too slow. At this point, you can profile the rendering. So it depends on your front-end framework. But here, in the case of React, you can use the React profiler. And in this case, I got an interesting problem. When I was opening or closing a tab, I had the whole thing was taking like 1 second to be done. And when using the profiler, you can see that it's displaying every component that is re-rendered while you're doing interactions. And only the components that are colored on the graph are actually re-rendered when you're doing the interactions. And you can see that on the left, I had a whole set of components that was the component displaying the project manager. So the project manager, it's a bit like a file explorer. And this thing was being re-rendered every time I was switching to one tab to the other, even when it was hidden. So the solution was to add something like should component update or memoization, so that it's not re-rendered every time you're doing any interaction. So basically, avoid re-rendering if you don't need to. Something to note is that make sure to measure performance in production, because in the case of React, the development build is way slower than the production build. And something that I got an issue where I was drag and dropping things, and it was taking like 1 second again to update, but it was a few milliseconds once I built the whole thing in production. You can also have issue with the calls to WebAssembly. So if you have lots of calls being made to WebAssembly, you're paying the cost to go through the bridge between JavaScript and WebAssembly every time you're calling a function. This is less the case, I think, now, because I think that Firefox at least has been optimizing this use case. But if, for example, you have a list of lots of objects, and every time you're mapping on the list, you're calling a function, at the end, it can add up. It won't be noticeable, in fact, in most situations, but something to remember that sometimes might be helpful to store in the JavaScript world, to cache in the JavaScript world the result of some computation if you want to avoid paying the cost to go through the bridge to the WebAssembly world. Sometimes you're reaching a point where your code base is growing a lot. So a few tips on this. In my case, it was because as it's an open source project, I got more and more contributors. The first thing I will tell is to stick to your components. So the idea is that if you have an help button that is showing, allowing you to open the help of the software, you might think at some point, okay, let's change the design of the help button so that it's smaller on screen. So you could add just a font size that is different. What I would recommend is to make an help button, a separate component, basically to create components for as much things as possible. In other words, make a design system and try to stick to it. Because once you've been doing this thing, it will be much faster to build new screens and consistent screens. Something that I don't know is I'm not doing any unit test. Sorry. Actually, I do, but only if there is a bit of logic in my component. And I think it's the case in almost, it's really very rare that I'm doing a unit test for a React component. Instead, I'm creating visual stories. So using, for example, Storybook or React Style Guidist, you can create stories that are displaying your components outside of your application. And I found this pattern to be really faster and way more powerful to first develop components outside of the application. And so you're much faster because rather than having to launch the application and then to navigate to a screen to see that your changes are applied or not, you just have to run Storybook and go to the proper story. So it's much faster for development and also for testing. It's not automatic, but imagine that in the future I'm updating Material UI, or I'm making changes on the component. I can quickly open Storybook and see my component in different state and make sure that everything is correct. It's in particular useful for cases like, for example, the errors handling. If a component is showing an error, that's something that you're never seeing the errors when you're developing because everything's going all right. But at least using Storybook, you can make sure that your components all have an error state that is working. The next advice will be to use types. So for example, Flow or TypeScript. In my case, I've been using Flow because I was more used to it. And the useful thing with types is that they will tell you when you forgot to pass or remove a prop after refactoring something. They will help auto-completion, avoid silly mistakes, and help to document your objects. All these things are not useful when you write code, but later when you're back on some module that you or someone else wrote a few months ago. And in other words, types are really shining when you or someone else is coming back and refactoring some part of the application. And remember that after a few months, you are a stranger to your own code base. So this being done, we now have both the core of the software and an interface that is being made on top of it. And let's see how to package this. So we have a few packaging options. We could make a PWA because WebAssembly is running in the browser, so it's not an issue. In my case, I've been using Electron so that I can have access to the file system. And also because it's a game editor, people like to download an application to own it in a way. And having access to the file system allows me to avoid making something that is only working online. So we can use the software offline. And in some case, you can even embed the JavaScript application inside the native application using, for example, Chromium embedded framework, if you have an existing native application and have the manpower to do it. Another advice would be to build over the native API as much as you can. So for example, I did two versions of the context menu, one that is using on the left the Material UI context menu so that it's running in a web browser. And on the right, you can see the same context menu using Electron APIs. So you have a real context menu. And I won't go through the code, but the idea is that instead of rendering some Material UI components, I can call the Electron API to create this context menu. And this is something that is really helpful for people that, not helpful, but that makes the application looks like a native application. It does not look webbish. And yeah, we can wonder now what's the result of all of this. Let's take a look. So this is a new application, and the demo I'm doing here is the same as before. I will be creating a button object with two animations, one when it's pressed and one when it's not pressed. And I will be adding it on the screen after renaming it to button, and doing the same thing as before, adding an event so that when the player is stepping on the button, then the platform is going up in the air. So that's the same, more or less same interface as before, but all done in React, WebAssembly, and JavaScript. So here I'm choosing the player and the button. And if there is a collision between these two objects, then I'm adding two actions. This time, the first one to add a force so that the platform is going up in the air. And then another action so that the button is going to the state where it's pressed. So changing the animation, that's how you do it. And when I will be pressing play, same as before, the WebAssembly module is compiling the whole thing to JavaScript, outputting files, and you get a working game in a browser. So yeah, that's working. Or at least in my definition as a developer, it's working. But what are users saying? I will be honest, the first feedbacks were really bad, but not because it was an Electron application or built using React or because it was web technologies. It was just because the new version was lacking a lot of features from the previous one. Even if I did reuse the existing code base, I had to remake the whole interface around it. So of course I started by a few things and adding new things. So it was lacking features, but after after 1 year precisely, people started to say, okay, there is a real difference and it's easier to use, and actually I can be more productive using the new version compared to the old one. So it works. It works so well that it's now even better than the native application. Why better? Because I can do ultra-fast iteration on it. I can test super easily. I have a near perfect cross-platform, and I have a faster startup time. It's faster. I have auto updates, more contributors. We can try it online, and we can even run it on phones. I mean, it's running on a phone. It's not made for a phone, so you cannot really use it properly. I mean, you can use it properly, but it will need some enhancement to do it. But my point is that it's working almost everywhere. So with this talk, my idea was to show that actually we can do things using React, WebAssembly, JavaScript, and all these new front-end framework. We can do things that are not only as good as what we used to do in the native world, but we can be more ambitious. Thank you.